Well, hey there. Welcome to Doc Onco's Physics. Keith Onco here. Today what we're going to be looking at is yet another projectile motion problem. This one's a little bit different, but it's really analyzed in the same way. What we have here is a word problem that says that the pilot of an airplane traveling at 180 kilometers per hour wants to drop supplies to flood victims isolated on a patch of land that's 160 meters below the plane. How many seconds should the supplies be dropped before the plane is directly overhead the people? Okay, so first what we'd like to do is collect our data in the table. So we have a velocity of our airplane. Whoops. Let's switch that to there. We have the velocity of our plane at 180 kilometers per hour horizontal. Okay, so our plane is traveling at 180 kilometers per hour in a horizontal direction. Well, first we're going to need to convert that to meters per second. All right, so this is the same as 180,000 meters per hour. All right, and if we divide this by 3,600, which is the number of seconds in an hour, we get a velocity, a horizontal velocity of 50 meters per second. So that's the velocity that our plane is traveling in the horizontal direction. So I'm going to add that to our table here, 50 meters per second. Okay, and that is also our final velocity in the x direction for our airplane. Okay, because remember, any of these projectile motion problems that we're doing, and we're going to consider this to be a projectile motion problem. The initial velocity in the x direction, the final velocity in the x direction are going to be zero as long as there's no other, there's going to be the same as long as there are no other forces acting on that projectile. And it's not really the plane that is our projectile of interest here. It's going to be a package that gets dropped from the plane. Okay, so the instant that package gets dropped from the plane, there are no other forces acting on that package. Okay. So what's the initial velocity going to be in the y direction? Well, at the moment that the package is dropped, remember, anytime we drop something, the initial velocity is just going to be 0 meters per second. Now, it gains velocity as it travels downwards, all right, because it has an acceleration due to gravity, but the initial velocity when something's dropped is going to be 0. As is usually the case, we're going to take our coordinate system to be at x equals 0 and y equals 0. And so our initial position for x and y are going to be 0. Okay. Now it says that the plane is 160 meters above the surface of the ground. So if this is our x equals 0 and y equals 0 position, right where the plane is going to drop the package, then the package is going to be going in the downward y direction. And so when it finally hits the ground at some point, the position, right, the final position in the y direction is going to be negative 160 meters. Okay, because that's simply the way we've decided to do our coordinate system. This is 0, 0 up here, right? X equals 0 and y equals 0 up here. And so below that, we're going to be in the negative y domain. Okay, let's see what else we have. So we've got our initial velocity horizontal, right? It's going to drop supplies to flood victims isolated on a patch of land that's 160 meters below the plane. So what's the trajectory of our package going to look like? Well, it's going to look, something like that. So X marks the spot there. And what the pilot needs to know is how many seconds should the supplies be dropped before the planes directly overhead the people. So here's some range here, right? X final. The pilot's going to have to drop the package at some position, say over here, in order for that package to actually make it to the people on the isolated island or wherever they are. Okay, and so the pilot's going to have to drop that package long before, right, the pilot actually gets over the patch of land. Because if the pilot drops it once the pilot is over the patch of land, then remember, this is the trajectory. Here's the trajectory of our package. It's this, right? That package is going to land in the water somewhere. All right, we don't want that to happen. Okay. All right, so let's go back to our table of information over here. So in the y direction, we have initial position is 0. Our final position is at negative 160 meters. Our initial velocity is 0. We don't know the final velocity. Our acceleration is always negative 9.8 meters per second squared. We want to know how much time it's going to take for that package to hit the ground, right? Because remember, time in the y dimension is the same as the time in the x dimension. So if I can get the time in the y dimension, I know what the time is in the x dimension. So I know when that pilot's going to have to drop that package. Well, let's see. We have, again, x initial, we have x final, we have v initial, we have acceleration. All right, so we could use the top equation, all right, to find the time. We could also use the bottom equation to find the final velocity in the y direction, and then use that final velocity, plug it into that equation to get the time. So that would be a two-step process that we could use. But I'm going to choose to use the top equation instead. Okay, so let's do that. X final, which is going to be a negative 160 meters, equals x initial, which is 0 meters, plus v initial in the y direction, 0 times t, plus a half, times a, negative 9.8, running out of space here, meters per second squared, times, that's a 2 there, times time squared. Sorry for smushing the equation there. So we get negative 160 meters. It's going to equal negative 4.9 meters per second squared times time squared. All right. I divide both sides by 4.9, negative 4.9 meters per second squared. That's, let's see, 160, negative 160 divided by negative 4.9. And I get a value of 32.65 seconds squared equals time squared. All right. If I take the square root of that, 32.65, take the square root of that, and I get 5.71 seconds for the time. That's how much time before the pilot is over the land that he's going to have to, or he or she is going to have to drop that package. Now what if instead of knowing the time, I wanted to know the range? I wanted to know how far before the x range here, I want to know how far before the pilot is over the land in order to drop the package. Well, we can find that out now, right? Acceleration in the x direction is always 0. Remember that. That package has 0 acceleration once it's released. So we can use the same equation, right, but using our x information. So I'm going to go over here on the left-hand side and say that x final is going to equal x initial, which is 0, plus v initial times t. So that's going to be 50 meters per second times the time that we just calculated, which is 5.71 seconds, plus a half times at squared. Well, their acceleration is 0, so it's just plus 0. And so when we multiply 50 times 5.71, we get 285.5 meters. All right, that's going to be how far the pilot would have to drop the package distance-wise in the x direction before he got to the island, all right, or before he got over the island, in order for that package to actually drop on the island below. I hope that helps. Have a great day.